All right. So what we have is we're looking at permutations and combinations. And again, we're looking at really just fancy ways of counting. Like we're used to the idea that counting is, 1, 2, 3, 4, 5, and so forth. And what we're finding is that, well, if we're trying to figure out what a sample space is, all the possibilities that could occur after some event, it's actually really hard to do. It's not an easy thing to do with the sample space. So what we're going to look at are other forms of counting. But to do that, we're going to need a tool. And we're going to use this thing called factorial. So the way a factorial works, it's an exclamation point. Now this is sort of one of these mathematical operators that's sort of surprising. What it means is this. You can think of it as sort of an avalanche of multiplication. And we keep going. Like so. So let me give you an example of what this does. Five factorial. What this means is 5 times 4 times 3 times 2 times 1. So 5 times 4 is 20. 20 times 3 is going to be 60. 60 times 2 is 120. 120 times 1 is 120. And that's going to be your answer. So that's all that it means. You're going to take this number as the starting number and multiply it to all the integers, positive integers. Actually, we should say natural numbers that are below it. And let me show you kind of a special one. If you see something like this, 0 factorial, we define this as equal to 1. There's some mathematical reasons why that I really can't remember at the moment.
Sir?
Yes.
Which section are we on again?
Oh, we're section 12.2. We were going to cover 12.2 tonight. I don't know if we'll get to 12.3, but we'll take a look at 12.2. But this is sort of one of these, it's going to be a tool that we're going to use. Now, let me show you some other things with it. So let me go here. Let me pick something from, let's say we have this. Ooh. So 9 factorial minus 5 factorial. So what we're going to do here, remember, these are multiplications. So we're going to follow PEMDAS. We're going to do the multiplications first. Let me grab a calculator real quick. Because 9 factorial is not a trivial calculation. Now, if you have a scientific calculator, there's usually a factorial on your machine. And that's going to be your answer. Now, what we're doing here is, because this is multiplication, we're following PEMDAS. So we're going to do the multiplications first, then we're going to do the subtraction. Now, something else that could come up though, what if we have this? Now, in this case, you have parentheses. So what you're going to want to do is do what's in the parentheses first. So this will be 4 factorial, or just 4 factorial. Now, this is a little more manageable. This will come out to 24. So any questions about that? So we're going to encounter this sort of calculation tonight. And there's another kind of calculation we're going to run into also. Let's do this. Once again, we've got 9 factorial, which is not my most favorite factorial. Now, what we can do is expand this. Now, expanding it means putting it as multiplications. Now, what we want to do is save ourselves some trouble. Just like when you reduce fractions, if you see a number repeated in the bottom and top, you can cancel it. Same thing here. We don't have to actually compute this and then compute this and then divide. What we can do is cancel the 5s, the 4s, 3s, 2s, and the 1s. And what that leaves us with is 9 times 8 times 7 times 6. Now with a calculator, this is 3,024. And this kind of thing we're going to be doing tonight as well. So questions about that? All right. So first off, permutations. Now, permutations, I'm just going to use the definition from the text. It's objects in a definite order. So, for example, let's say we have this. One of these here. A scatter of things. Now, let's say we want to place this scatter of things no longer as a scatter, but in some kind of order, say a preference of sorts. Well, this would be considered this would not necessarily be a permutation, but this would. We would place this in some kind of order. So we could just have some objects floating in space. We could have, say, just sort of a group of people in a room talking or something like that. And let's say we're going to play some kind of game. You need to have someone go first, someone go second, someone go third, and so forth. We can take everything that's floating around, or every one, place them in some kind of order. In that order, this is one permutation. Now there could be others. You could do something like this. Sure you could see that? Okay. So this would be another permutation of these same objects. So one of the questions we're going to ask tonight is, well, here's a permutation, here's a second. Are there other ones we could come up with? Well, certainly we could do one where there's a triangle first, or another one with a square first. We could do that. How many of these how many of these exist? Well, let's take a look. So we have these four shapes. Now, if you recall 12.1, what we finished with, we talked about this idea of without replacement, say drawing something without replacement. So that means if you had 10 tickets in a hat and you drew out a ticket, you have 10 to draw from, and you choose that ticket. And you, say, record it and throw it away. When you draw your second ticket, you only have 9 to choose from. You choose a ticket, look at it, record it, toss it away. And now you only have 8 tickets to choose from for the next round. So when we decide permutations, when we're going to count these, we're going to count them again in stages. So stage 1. Stage 2. Stage 3. Stage 4. So how many objects do we get to choose from in stage 1? Well, there's 4 to choose from. Now, let's say we chose a smiley. That leaves 3 objects to choose from for the second object. Well, now we have 2 objects for the second object, or third object. And there's just 1 for the last object. So what we're going to get, the number of permutations where we take these and we create some kind of order, the number of different orders we can come up with will be 4 times 3 times 2 times 1, or 24 permutations. Now, in mathematics, we look for shortcuts. We're always looking for patterns that make our lives easier. So is there a pattern that we see here? Do we have to think it through every time, like a hat or drawing tickets kind of thing? No, we don't. Notice that we have 4 objects. We have 4 times 3 times 2 times 1. Well, that's just 4 factorial. So here's a formula. It's not in the text, but we'll use it to build the formula in the text. It's going to be this. So the number of permutations of in objects is in factorial. Questions about that? All right, well, take that as a good sign. So what they're going to get at in the book is we have in objects, but let's say we're only going to choose 2 of them. So let's say we're going to do this. Let's say we have 6 objects. And we're only going to choose, well, let's say 4 of them. Choose 4. So we're going to place these in some kind of an order. So to give sort of a visual example, let's see. Let's say we'll go back with our shapes. The smiley, the star, the triangle, the square, in no particular order. Something other than geometry. Well, we'll go with the letter M. Let's learn a little bit of Greek tonight. Let's do alpha. The Greek letter A makes the A sound in Greek. So we have our 6 objects. Let's say we're going to choose 4. So we'll take a star, alpha, square, and a smiley face. And we place them in some kind of order. 1, 2, 3, and 4. So that's what we're doing. We're just sort of reaching into this, collection of 6 objects. We're going to pull 4 out and then give them some sort of an order. Like we hand this out to the first place person. The second place earns an alpha. The third place earns a square. And fourth place gets a smiley face. Not sure what kind of subtext exists in this, but well, that's what you've got. So how many permutations, how many orders can we come up with if we're just drawing from all of these randomly, but we're only doing 4 at a time? Because we could come up with another permutation. We could go, and let's get someone who was left out. Let's get an M. Let's do a star. Put in another smiley face. Let's see, and we need the triangle. They didn't get to go yet. So this would be another permutation of 4 objects drawn from the 6. So how many of these can we come up with? Well, let's take a look. The way we're going to do this we have stage 1, stage 2, stage 3, stage 4. Now, for stage 1, how many choices do we have? Well, in this part of the experiment, we have 6. So we get to draw 6. For stage 2, we'll have 5. Stage 4, we'll have, stage 3, we'll have 4. Stage 4, we're going to have 3. So what kind of pattern can we get from this? It's a bit obscure. This is something that's kind of tricky. But let me show you a trick. What we can do, let's take in factorial. In other words, let's take 6 factorial. Let's just run the whole thing out. If we could somehow get the 2 and the 1 to cancel, like divide by 2 times 1, this works. So if we had this, these would cancel, and that gives us what we want. how can we get the 2 times 1? Now, I don't know who came up with this. This is really, really clever. But what you can do is this. We take n factorial, and then we take 6, which is the n equals 6, minus the number of objects we're going to draw. Now we're drawing 4 at a time. So 6 minus 4 factorial. Watch how this works. What's 6 minus 4? Well, it's 2. So you get 2 factorial. What does that become? I'm using x's instead of dots this time. But you're going to get the 2 numbers we want to see things cancel with. And so we get our 6 times 5 times 4 times 3, 120, which is 360. Now, I'll be honest, the way we did it in the beginning, 6 choices, 5 choices, 4 choices, 3 choices is a lot easier. But if you're dealing with some, well, we'll stick to the formula though. So how are we coming up with this? The pattern we saw was this. So if we have in objects, I mean, it could be people too. We're going to choose K. And the number of permutations is this. N factorial divided by n minus k factorial. And make a note. This is a little observation. If we're going to choose all n, like we started out with, remember when we did that? Well, how many permutations if you have different orders of everything? What was n factorial? So note, that would be n factorial over n minus, and we're using all n factorial, n factorial over 0 factorial, and remember that's supposed to be 1, which is n factorial over 1 or n factorial. So we still have our old formula. Now let's do some examples so you're not worried about this. So let's see. Let me see, we have a permutation one here. All right, we'll use the example in the text. Maybe we got, okay, we'll do the example in the text. So example 2, it's on page 698. And it says this: you have a tennis team with 6 players ranked 1 through 6. Now, the coach has 10 players to choose from to make this team of 6. So how many ranked teams can you put together? So you can choose the players from a group of 10 players. Now, a key thing with this problem is this last part. The last part's going to be this. How many ranked players, or ranked teams, I should say, ranked teams of 6 can the coach assemble? Give you a second to put that into your notes. Now, the issue here is ranked teams. And I'm going to bring it up a little later why you need to mention we're producing ranked teams, which seems kind of silly. Like we know who the first player is, second, maybe it isn't. But when they're not ranked, you don't have as many teams as you think. But let's say we have ranked teams. I'll explain why later when we get to combos. So what we have is this. We have 10 players to choose from. So N is going to be 10. Now, we're going to choose 6 of them and put them in a rank, in order, like 1, 2, 3, 4, 5, 6. So you can sort of think of it as, you know, this is the first player, they've got the best serve, and that's what wins all the matches, so we're going to make them the first player we're going to pick to play all of our games. And then you come up with who's going to be second and third and fourth and fifth and sixth and so on for whatever reasons. So N is 10, K is 6. So what we're going to get then so using our formula, we have 10 factorial over 10 minus 6 factorial, or 10 factorial over 4 factorial, because 10 minus 6 is 4. And we can drop the parentheses then. Or we have 10 times 9 times 8 times 7, using dots because they're smaller, times 6 times 5 times 4 times 3 times 2 times 1, 4 times 3 times 2 times 1. And now we can cancel things. And so now we get wow. So we double check my result here. Yes, that's correct. 151,200 teams. That's quite a few. So there you go. Now, sort of a tip is I'm canceling things to make the calculation easier. If you've got a calculator with a factorial, you could just do, 10 factorial divided by 5 factorial. It equals, and oh wow, let's see that. Oh, 4 factorial, that's what it is. So 10 factorial divided by 4 factorial. And you'll get the 151,200. So just using your calculator, using the factorial keys can be much faster than going through the entire process. So the point is, that's a lot of permutations from just 10 people. You can assemble teams of 6 that are all ranked. You get 151,200. So, golly, all right. Now, there is something we want to take a look at, and it's permutations of what they call indistinguishable objects. Let me see, am I spelling that correctly? Not dish. Indistinguishable objects. So let me show by an example. Let's say we have something like this. We have objects B1, B2, and we have object C1. Now, how many different ways can we order these? Well, we would, if we wanted to order, say, all of them, all 3 of them, we could say 3 times 2 times 1, or 6. Or we could do 3 factorial over 3 minus 3 factorial. I'll slow down, sorry. So they're just sort of maybe kind of, hopefully not confusingly ordered. Like this is the first B, the second B, but if we're going to come up with any order we want, we can switch the order on those. We can move this C around all kinds of places. And how many different versions of this would we get? Well, we would get 6 versions of those. Now, what happens though, and here we can actually go through all of them. If you do all of them, what you'll get is B1, B2, C1, B2, B1, C1, and then let's go B1, C1, B2, B2, C1, B1, C, B1, B2, and C, 1, B2, B1. So there's the 6 different ways we can reorder these objects. Now, these are distinguishable. Now, what we mean by distinguishable is that this B1 and B2, we can see that there's a B1 and there's a B2. We're not going to accidentally switch them around. Like, wait, is that B2? Oh, no, that's B1. We can distinguish it from B2. Now, what happens, though, if they're not distinguishable? In other words, we couldn't tell the difference between B1 and B2. So if we take this one here and this one, we get BBC and BBC. Well, is this B2? Is that B1? Is this where B1 is in front of B2? We can't tell. We're going to get into similar issues over here. Again, is this where B2 and B1, or is this B1 and B2? Can't tell. And then again, same situation. So these right here, these are distinguishable. These here, indistinguishable. So here's the thing. When they're distinguishable, we clearly have 6 different results. If we were, say, playing, what's that game where you have in Las Vegas, where you have the wheels and you pull the lever and then the wheels go. And we could pull the lever and we get B1, B2, C1. Pull the lever again, we get C1, B2, B1. But down here, and let me emphasize again, we say we pull the lever, we get this. We pull it a second time, we get that. These are clearly different. But when you remove the subscripts, they're the same. So if you were flying to Las Vegas, and you've been to the Las Vegas airports, and you see those machines there, where you have the wheels and you pull the lever, this would be a different result than this. But if the subscripts were rubbed off, they would look like this. It would look like you're getting the same thing twice. So here's the question we're going to try to figure out. Here we have 6. So let me, there we go. So for distinguishable, there are 6 unique outcomes. But for indistinguishable, there are only 3 unique outcomes. So the question is, how do we count these indistinguishable outcomes? And so I'm going to give you a formula that lets you do this. So what we're going to do, the formula is going to be this. It's kind of a complicated one. But we're going to take the number of objects, which was 3. Let me see. Let me take a look at that. Let me check my formula here real quick. Oops, sorry, I think I just wrote down the wrong formula. My apologies. Let me take a look. Oh, no, we're fine. We're fine. Okay. So what we're going to do is this. We're going to take n factorial. And we're going to divide by the factorial of the number of types that could be confused with each other. So N is the total number of objects. So in this case, it would be B1, B2, B3. I'm sorry, C1. Now K1 is the number of B objects. Now B objects is a pool of objects that if we remove their subscripts, they become indistinguishable. So how many B objects become indistinguishable? Well, there is B1 and B2. And then finally, K2, it's the number of C objects. There we go. That was just C1. Now, does this work? I'm just going to give you this formula, and well, let's see what happens. Well, the number of N objects, B1, B2, and C1, well, that's 3 factorial. The number of K1 objects, B1 and B2, well, that's 2 objects, so 2 factorial. And then the number of K2 objects, well, that's just the number of C objects. Well, that's just 1, so 1 factorial, which is just 1. Now remember, what we're going to be doing is we're removing the subscripts off of these for this formula. So technically, we just have a B, and a C, a BB, and a C. That's it. So when we take the subscripts off, that's when we use this formula. And so what do we get? Well, we should get only 3 types. There's only 3 kinds of things we're going to see when we pull that lever and the wheels roll. There are only 3 kinds that we would see that would be different. Well, 3 factorial is 6. That's what was throwing off my formula. And then this is 2 times 1, 6 over 2. 3. So the formula does work. And again, I'm just giving this one to you. Now, in general, this is what we've got. So if we have N total objects, of these N objects, they're divided into R groups. And all the objects in a group are indistinguishable. We've removed the subscripts. So this is our setup. We have N total objects. We divide them into R groups. And so all the objects, this is our collection of objects. We're going to divide them into groups. And all the objects in a single group, they're indistinguishable from each other. Now they might be clearly different from objects over here. Like these could be red marbles, these could be green marbles, but the green marbles will all look the same, red marbles will all look the same. You can't distinguish one red marble from another. So let's do this. We're going to make a note. Let Ki, or let's not go with I, let's say K1 equal the number of objects in group 1. And let K2 equal the number of objects in group 2. And so on and so on. Remember, there are objects. We have group 1, group 2, group 3, until we get to group R. So KR is the number of objects in group R. So the one thing we want to make an observation about, if we take all the objects in all these groups and we add up the populations of each group, they should add up to the total population. So that means K1 plus K2 plus KR is equal to N. So finally, what is the formula we're getting at? We just sort of broken things up. Well, the formula is going to be this. If we want to find, let's see, the number of permutations So we're going to do permutations of these n objects. What it's going to be is n factorial divided by K1 factorial, K2 factorial, KR factorial. So questions about that? It's kind of a tricky formula. So let's do an example. Okay, we're doing good on time. So let's say we have this. So let's say we've got a password here that requires, I'm following the example book, example 5, a password requiring 7 characters. If a person who lives at 155 Newton Road wants a password to be as an arrangement of the characters of that address, how many different passwords are possible? Let me show you what we're doing. You're using these characters, now we're ignoring spaces. Now, why this is a question is, why can't we use the old permutation formula of, well, there's 7 here. Why not 7 factorial, 6 factorial, and so on? The reason is if we switch the 5s and we use that as our password, well, let's say we use this as our password. Start off with this. But then we switch the 5s, we still have the same password. So, and the same thing, if we switched any of the ends, we still have the same password. So just because we switch something around doesn't mean we've changed the password. So we're not generating as many passwords as we think. Now, this is the whole issue with the ranked players. You see, let's say you choose 6 players and they're ranked 1 to 6. And let's say you switch player 1 and player 6. You switch them like that. When we're talking about ranks, you now have 2 different teams. Like let's say you switch Sally and Bob, and Sally is number 1, Bob's number 6, and you switch it so Bob's number 1 and Sally's number 6 for some reason. Well, you have 2 different rankings now. So you have technically 2 different ranked teams. But if you have Sally and Bob, and let's say they're just sitting on benches and they're not ranked, just 6 players, and they're sitting on some chairs, and you have Sally and Bob switch chairs, you still have the same team. So that means when we don't distinguish between players and we just move things around, we still have the same team. So this is kind of the same idea. In this case, if we switch the 5s, we still have the same password. We switch the ends, we still have the same password. Now, if it was like this, though, it was 5152, and for some reason the computer, you could put subscripts on these, then if we switched them, we would now have another password. But since they don't have subscripts, switching the 5s doesn't change the password. So let's break this down. First off, what is our N? Well, N, we have 7 characters to choose from in total. So N's going to be 7. Now, how many groups do we have? Well, for R, we have a group for 1. We have the 5 group. We have the N group. And we have the U group. So there's 4 groups. So R is going to equal 4. So we have N, we have R. So we're going to have 4 groups. So let's take a look at our 4 K groups. So K1, let's let that be 1. Now, how many 1s are there? Well, there's only 1. Now for K2, let's let K2 represent the 5. Well, how many 5s are there? Well, there's 2. Now for K3, let's let K3 be the N group. How many N's are there? Well, there's 1, 2, and 3. So we got 3. And then finally, K4, this will be the U. How many U's are there? There's only 1. So now we can use our formula. How many passwords are we going to be able to generate that are legitimate passwords, legitimate different passwords? We'll do N factorial over K1 factorial, 2 factorial, 3 factorial, K4 factorial. So N is 7. Now, K1, there's only 1, so that's 1 factorial. K2, there's 2 5s, so that's 2 factorial. K3, there's 3 N's, 3 factorial. K4, there's 1 U, 1 factorial. So let's actually do this one. We'll hammer it out. So 7 factorial, 5040. 1 factorial is 1. 2 factorial is 2. 3 factorial is 6. 1 factorial is 1. So we'll get 5040 over 12. We'll get 420. Double check my solution there, that is correct. So you could get 420 unique passwords by switching the characters around. And that means that you have to kind of discount or not count some passwords that, well, you switch the characters around, you're really just getting the same password. So this brings us to the last thing in this section, and it's called combinations. For combinations, order doesn't matter. So this is the situation where you would ask, let's say you have 10 players and you're going to choose 6 of them. And when you choose the 6, you're not going to rank them. We're not going to ask for how many ranked teams are there. Because again, if you switch the first person and the 6th person, now you have a totally different team from what you started with. But in a combination, switching the person sitting on this end of the bench, the person sitting on the other, since in combinations, order doesn't matter, well, then you haven't changed the team at all. It's still the same team. It doesn't matter where anybody sits. So that's the idea of a combination. So the way we handle combinations, it's very similar to the formula we just saw for these different R groups or objects within each group are not distinguishable from each other. Think like red marbles, blue marbles, green marbles. That's sort of the classic example. So what we're going to do with combinations is going to be this. You're going to break it down basically into 2 groups. Instead of R. So we could say K1, our first group, are the number of objects we want to choose. I'm going to say we chose. So in this case, what we do is we choose some objects, and that becomes a group. That becomes our K1. Choose how many objects. The objects left behind automatically become K2. Actually, I'm using this a little differently. I'm just going to say objects we choose, and then objects we didn't choose. So basically, whatever population we're dealing with, we break it into 2 groups. The first group is whatever objects we happen to choose. And the second group is, well, that's the objects we didn't choose. So the formula we're going to get is this. Let's say we're going to choose K objects. Then the number of combinations it'll be n factorial, K1 factorial, or times K2 factorial, or now we're choosing K objects. So that means K1 will just be the number of objects we chose. That's K. Then how many objects did we not choose? Well, the number of objects we didn't choose would be n minus k. That's how many objects are left over. And so that means we're going to have this. This is the formula we're going to use. So again, we choose, there's going to be n objects. K objects chosen. N minus k left behind. So we have two groups. Whomever or whatever we chose, and then whomever or whatever got left behind. Those are the two groups. So let's do an example. So let's say we have this. So let's say we have this, and this is example 6 in the text. An emergency room at a hospital has 11 nurses. So 11 nurses on staff. Now, each night, a team of 5 nurses is on duty. So how many teams or how many possible teams are there? So one of the things with these questions is sometimes it's a little tricky figuring out what they're asking for. Are they asking for a permutation or are they asking for a combination? And the thing is with permutation, remember, order matters. And for a combination, order doesn't matter. So order matters, order doesn't matter. So looking at the question, does the order matter? Are we ranking nurses? Like say, for example, which nurse can, say, get here faster from home for some reason? For example, let's say you leave your shift and you go home, and if for whatever kind of work you were doing for some reason, if you might get called back, or if there was some particular situation on that shift where, okay, when people are leaving the night shift, we might need to call you back right away if you get home because someone can't make it in the morning for some reason. So maybe you'll rank the nurses and sort of like, well, who's closest, next closest, next closest, who's farthest, and so on. So you might rank nurses like that. But are we ranking any nurses? It looks like we're just trying to pick 5. Like if you have a hat, put 11 names in a hat, pick out 5, and that 5 is the group you chose. That's your K. And then the leftover group, the group that's going to have the night off, that will be your N minus K group, the group you didn't choose. So that's exactly what we have here. The order doesn't matter. So how many teams do we have, could we pull out of this? Well, the total N is 11. We're going to draw 5. So our K is going to be 5. And then our N minus K, which will be 11 minus 5, that's going to be 6. So now let's use our formula. and what we could do. Let's see. They'll go through the whole calculation. We'll do the same. We get more room. So again, look for cancellation. Let's see, we can get the 6, 5s, the 4s, the 3s, the 2s, the 1s. And we could do some other cancellation, like 5 goes into 10 2 times. 3 goes into 9 3 times. 4 goes into 8 2 times. There's another cancellation. So 42 times 11, I'll break down into the calculator. 462. That's going to be your answer. I'll double check that. Bingo. Well, that's it. That's 12.2 with 3 minutes to spare. So again, if any questions about this section, let me know. You have the weekend for the exam, so that'll be on Tuesday. And then we'll take a look at section 12.3, and we're getting close to wrapping things up. We have sections 1.1. Let me see, do we have, what's it, 1.1 and 1.2, I think. Let me see. 1.2 and 1.3, and then that's going to be it. So we'll just go from there. There's 2 more lectures. We might do 1.2 and 1.3 in the same. We'll see. But that's it for tonight. So if you have any questions, let me know. Have a wonderful evening.
Bye, sir. Take care now.
Bye, Justin.